So just a quick review of what we covered in class today. We were talking about linear versus nonlinear functions. And aside from identifying functions, just about everything we've done in class so far has been examples of linear functions. And when I keep saying functions is just applying a new vocabulary and a new use to the equations we've already been using, again, I'm talking about linear equations and linear functions. But functions are much broader than that. We focus on linear functions here to get our feet wet, to kind of understand what we're doing with it. But there are many, many functions that aren't necessarily linear. So we're going to talk today about how to identify. Just one way to classify functions. Are they linear functions or nonlinear? So quickly, a linear function, if you look inside there, you see that word line. Linear always means line. So a linear function is a function that will make a straight line when we graph it. Okay. So a linear function graphs a straight line. Another way to look is an equation is linear if it can be written in the form of y equals mx plus b. And we keep coming back to this slope-intercept form throughout this unit and the previous ones. But if you can take an equation and rewrite it into y equals mx plus b, then you know it's going to be linear. When you have this, m is the slope and b is the y-intercept. But it's very important to notice in y equals mx plus b, there are no exponents, right? X is to the first power, y is to the first power. There's no exponents greater than 1. And that's a pretty good rule of thumb. If you don't see exponents, then the function is a linear function. There are a few exceptions to that rule. But pretty generally, if you see exponents, then it is a nonlinear function. And then a table is linear if it shows a constant rate of change. And if you look between these, a straight line means that the slope is constant, a constant rate of change. In order to write an equation in this form, y equals mx plus b, you have to have the slope being just one number. So all of these three are kind of repeating each other. But it's just different ways. We talked about different ways to represent a function. And here are different ways to tell if it's a linear function. We tell you how to do it if it's a graph. You look at the picture. Is it a straight line? We tell you how to do it if it's represented algebraically or as an equation. Then you look, are there any exponents, right? Is it in the form of y equals mx plus b? And we tell you how to do it if it's written as a table or numerically. So these are three of the representations that we've talked about for functions. And if you look at each of those representations, how can you tell if a function is linear or not? So these are the things to look for. So if you get that down, we can go and look at some examples. Here are two examples. I have a function written here algebraically. I have a function written here. What I'm going to do is fill these in so you can see how it looks on a table and how it looks on the graph, and then we can talk about what we see. So negative 2 to the second power is 4, plus 1 is 5, negative 1 squared is 1, plus 1 is 2, 0 squared plus 1 is 1, 1 squared plus 1 is 2, and 2 squared plus 1 is 5. So this is what my table looks like, 5, 2, 1, 2, 5. This is a function, right? Every input is associated with only one output, but you may notice that these numbers follow a pattern. Similarly, if I start to graph these, you can see, a student said they thought this looked like a triangle. It kind of does, but the shape of this line is actually more curved than a triangle. It's more of a U shape. It is what we call a parabola, parabolic curve. So whenever you get this x squared, it is a parabola. Okay, so then let's just very quickly look at this other one, and then we can talk about how they compare. Y equals 1/2 x. If I put in negative 4, I would get negative 2. Negative 2 would give me negative 1. 0, 2 would give me 1, and 4 would give me 2. Right? Again, it's a function, one input, one output for every input, and I can go ahead and graph that. Should be able to make this a fairly straight line right through there. Okay. Right. So if you look at these, the black function and the red function, what are some things that we see? I think if we look at the pictures, it's very obvious to start with that this black function is not linear. It is not linear. That is not a straight line in any way, shape, or form. So the next thing we want to do is look and see what are some clues even before we got to the picture that this wouldn't be linear. And one of them is, I erased my lines here, but I see this x squared. I see an exponent. If there is an exponent, it is not going to be a linear function. It cannot be. So that is one clue. Another clue is here in the table. Every one of these x values, I just increase by 1, right? I'm just adding 1 to move up this table. So my x values increase by a constant amount. These y values, first I subtract 3. Then I subtract 1. Wait a minute, then I add 1, and then I add 3. This is definitely not an example of constant change, right? So this is non-constant change, changing all over the place. So I could have looked at the table, and when I saw these numbers first going down and then going back up again, this is not a linear function. If they decrease and then increase, that's a clue this is not linear. So those are some ways to identify the not linear functions. If you look at this red function by comparison, I still go from negative values to positive on the table, but this one clearly makes a straight line. So this one is a linear function. I probably could have told that looking at this equation, because I could rewrite this as y equals 1/2 x plus 0. This definitely looks like mx plus b. Y and m only have the first power in them. So this is an example of a linear equation. And this time my values change by 2, but my x values are still constant changes, 2 every time. My y values, though, I'm just adding plus 1, I'm continuing, plus 1, plus 1. So this is an example of constant change. It's the same every time. And in fact, if I look, my y change is 1 over my x change of 2. You might see that that is the same m that was represented up in the function. So these are just some examples of how you can apply these rules that we talked about for a graph, an algebraic representation, or a table to tell whether something is linear or nonlinear. So we can look at a few more examples here. These are already filled out. This one was nonlinear. Is it functional? Is this function linear? No. And you could see right away there's an exponent. It's x to the third. It's nonlinear. This function, it turns out, is linear. You can see there's no exponents. It makes a straight line. But this one is the one I really want to review with you, because if you look at this, it's a little harder to tell. Y equals 12 over x. It looks like there are no exponents there, right? I don't see a squared, I don't see a cubed, but you have to remember that this is 12 times 1 over x. There is no way for me to rewrite this function in the form of y equals mx plus b. And what I said in class was to watch for hidden exponents, right? It's hard to see it, but I could have rewritten this as y equals 12 x to the negative 1. So there is a hidden exponent. So be very careful about just applying the exponents rule, because if you look at this graph, it is clearly not a linear function. So now I will swing back up here to these rules in case you didn't get a chance to get them totally down, but that is how you can tell a linear versus non-linear function.